Okay, so in the last video we got to developing the Lagrangian equations of motion, and so now I just want to do a bunch of applications. Alright, so let's throw a rock. So we'll project it. We know it's going to go into a parabola, but let's just see how that goes. Alright, so we know that we're going to be constrained to be in a plane, so our coordinates that we want to choose are just x and y. The potential energy is mgy. The kinetic energy is 1/2 m x dot squared plus y dot squared. All right, so the Lagrangian equations will be partial L partial x minus d dt of partial L partial x dot equals 0, and partial L partial y minus d dt of partial L partial y dot equals 0. All right, so for the partial L partial x, should probably observe somewhere that L is equal to t minus v, so it's 1/2 m x dot squared plus y dot squared minus mgy. All right, with that public service announcement out of the way, let's go ahead and do this. All right, no x dependence whatsoever. So we have 0 minus, okay, partial L partial x dot. The only thing that's going to matter is this 1/2 mx dot squared term. Differentiate that. The 2 comes down, cancels the half, leaves me with mx dot. Differentiate that with respect to time. I get mx double dot equals 0. All right, in the land of y, I differentiate L with respect to y. I get minus mg. And differentiating that, I get a 1/2 m y dot squared. Differentiate that with respect to y dot, I get my dot. Differentiate that with respect to time, I get minus my double dot equals 0. All right, so this gives me x double dot is equal to 0. Therefore, x dot is equal to some constant. Let's call that x naught dot. So we get that x is equal to x naught dot t plus x naught, integrating that. All right. Over here, we get that y double dot is equal to minus g. So integrating, we get that y dot is equal to minus gt plus y naught dot. Integrating that, we get y equals minus 1/2 gt squared plus y naught dot t plus y naught. Okay, so we've recovered the basic kinematics equations we've seen before. All right, let's do another example. Let's do a simple harmonic oscillator. So we got a wall. We attach to the wall a spring constant K. Attach a mass M. We'll pull it out some distance x and let her rip. Or I should say the position with respect to equilibrium is x, so that's our one and only coordinate. So t is 1/2 mx dot squared. V is 1/2 kx squared. Lagrangian is t minus v is 1/2 mx dot squared minus 1/2 kx squared. Our Lagrangian equation of motion is partial L partial x minus d dt of partial L partial x dot equals 0. So partial L with respect to x, that's going to bring down a 2 to cancel the half, leaves me with minus kx. Let's see here, bring down the 2, gives me mx dot, differentiate with respect to time gives me minus mx double dot equals 0. So that gives me x double dot plus k over mx equals 0. And we know how to solve that. We recognize that that is omega squared, so therefore simple harmonic motion with angular frequency root k over m, as we've seen before. All right. So those, you could argue maybe it's a little faster than doing it with Newton's second law. But let's go where the Lagrangian equations of motion really shine is when you start getting to things that are uglier. So let's say we have a rotating massless rim here, rotating at omega, and I have an attachment point here to which I hang a pendulum of mass m. Massless rod, of course. We'll keep it simple for now. All right, so we'll say that this is length A. That angle there is omega t. This angle here is theta, so that is my generalized coordinate right there. And we'll say the length of the pendulum rod is b. Okay, now this is a case where it's probably easier to play the game of let's do everything in Cartesian and then clean it up. So let's go and do that. So x is equal to a times the cosine of omega t plus b sine theta. Y is equal to a sine omega t minus b cos theta. All right, differentiating x dot will be equal to minus a omega sine omega t plus b theta dot cosine theta, and y dot will be, by the same token, a omega cosine omega t plus b theta dot sine theta. All right. So we know that the potential energy is equal to mgy. So they'll be equal to mg times a sine omega t minus b cos theta. That's about as clean as you can make that. But that's how you express it in terms of the generalized coordinate anyway. And the kinetic energy we can write as 1/2 m x dot squared plus 1/2 m y dot squared. So let's go start putting in on that. That'll be 1/2 m times, okay, we gotta square that. So that's going to give me a squared omega squared sine squared omega t. The cross term will be minus 2ab omega theta dot sine omega t cos theta plus b squared theta dot squared cos squared theta. All right, oops, we don't want to close the parentheses just yet. We can pull out a 1/2 m here, so let's just roll on the y dot squared. It'll be very similar, plus a squared omega squared cosine squared omega t plus 2ab, 2ab omega theta dot cosine omega t sine theta plus b squared theta dot squared sine squared theta. All right, well, for what it's worth, sine squared plus cosine squared is 1, cosine squared plus sine squared is 1, and I can pull a trig identity out of my butt for this one. So we get 1/2 m a squared omega squared plus b squared theta dot squared plus 2ab omega theta dot, and cosine omega sine omega t cos theta minus, I'm sorry, cosine omega t sine theta minus sine omega t cos theta is the sine of theta minus omega t. Whew. All right. So the Lagrangian is t minus v. So that'll be minus, so it'll be, sorry, 1/2 m a squared omega squared plus b squared theta dot squared plus 2ab omega theta dot sine of theta minus omega t. Minus mg a sine omega t minus b cos theta. All right. So we can write our equation of motion. Partial L partial theta minus d dt of partial L partial theta dot equals 0. All right. So constant, doesn't matter. Theta dot's constant with respect to theta. Okay, that term has got some thetas in it. So we're going to get from that an m times ab omega theta dot times the cosine of theta minus omega t. Let's see. Theta dependence here. So we get a minus mgb sine theta. All right, now differentiating with respect to theta dot, that's going to cancel our 1/2 there, so we get minus mb squared theta dot, but then we differentiate with respect to time, so that becomes theta double dot. And then we get minus, from here there's a theta dot term, so we get a minus m a b omega times theta dot minus omega cosine theta minus omega t. There, that looks better. All right, well, for what it's worth anyway, this term here cancels that right there. Oops, I'm sorry, I forgot to write 0 equals, so we're left with 0 equals g. We can divide the bunch of stuff out and clean it up a little bit, and you get g sine theta plus b theta double dot minus ab omega squared cosine of theta minus omega t. All right, and then we can get that into standard-ish form. We can write that as theta double dot equals ab omega squared. We'll be dividing by a b squared, so cancel, cancel. Cosine, sorry. So we have ab omega squared cosine theta minus omega t minus gb sine theta, right? Oh, right, and then we have to divide through by b squared, right? Yeah, that's a b squared there. So yeah, then I have to divide by b squared here and there. Cancel, 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 cancel. All right. Now, in general, this is going to be a bearer to solve. But if omega is 0, right, then this will reduce to theta double dot plus g over b sine theta equals 0, which is a simple pendulum. So there you go. But in any event, we've got an equation of motion we can put in. This would be something, I mean, it wasn't pretty doing it this way, but to do it with Newtonian mechanics would have been a total bear. Okay. So another example where we can start to think about non-inertial frames. So we can talk about a pendulum that's in an accelerating railroad car. So we've done this problem before. So let's say this is where, so we're accelerating forward at A. So this angle here, we'll call theta E for equilibrium. And we'll say that it's swung over here at this exact moment, and we have that angle theta right there. All right, well, the obvious coordinate is theta. Let's go and do this one by the Cartesian approach to generate our lines. So we know that x is equal to v naught t plus 1/2 at squared. That is the x coordinate of the train as we accelerate, plus L sine theta. Our y is equal to minus L cos theta. So x dot will become, differentiate that, v naught, differentiate that, plus at, differentiate this, plus L. Derivative of sine is going to be cosine, so we'll get an L theta dot cosine theta from that. All right, differentiate this with respect to time. We get y dot equals plus L theta dot sine theta. Okay, so the kinetic energy is 1/2 m x dot squared plus y dot squared. So let's start adding them up. So 1/2 m v naught plus at plus L theta dot cos theta squared plus 1/2 m L squared theta dot squared sine squared theta. All right. And v is equal to mgy, which is equal to minus mgl cos theta. And I'm not going to expand these yet. We're going to leave it like that. So L is equal to t minus v. So it'll be 1/2 m v naught plus at plus L theta. Oops. This L theta dot cosine theta squared plus 1/2 m L squared theta dot sine squared theta minus v means plus mgl cos theta. All right, so that's our Lagrangian. The Lagrangian equation of motion is going to be partial L partial theta minus d dt of partial L partial theta dot equals 0. So I'll leave it as an exercise for you to do the derivatives, and it turns out you'll get an epic amount of cancellation happening, and when you do, you will eventually end up with theta double dot equals minus g over L sine theta minus a over L cos theta. So we can find our equilibrium angle. We would demand that theta dot double dot be equal to 0 there. So be minus g over L sine theta minus a over L cos theta. We can just multiply both sides through by L, make that go away. And so we will have minus g sine theta equals a cos theta, or we get that theta equilibrium here, or the tangent of theta equilibrium is equal to minus a over g, which comports nicely with when we did this same problem in the chapter on non-inertial frames. Okay, so at this point, probably a coordinate shift makes sense. If we have an equilibrium, a new equilibrium position, it probably makes sense to redefine our variables, so that's what we're going to do. We'll let our old theta be equal to theta equilibrium plus some angle off of it, eta. So that'll give me, wherever I have theta double dot, that'll be equal to eta double dot. So my equation of motion will become, my theta double dot there will become eta double dot equals minus g over L. This becomes sine of theta equilibrium plus eta minus a over L cosine of theta equilibrium plus eta. All right. So if we use our angle addition formulas, we'll get eta double dot equals minus g over L times sine theta equilibrium cos eta plus cos theta equilibrium sine eta minus a over L times cos theta equilibrium cos eta minus sine theta equilibrium sine eta. All right, so following sort of the usual prescription, we'll just go ahead and look at this for the case of if eta is equal to small. Then the sine of eta is approximately eta, and the cosine of eta is approximately 1. So eta double dot becomes minus g over L times sine eta, cosine eta being 1. We'll replace that with an eta, so plus eta I'm sorry, not sine eta, sine theta equilibrium. Cos theta equilibrium minus a over L cos theta equilibrium then cosine eta is just going to be 1 minus here the sine of eta is going to give me just an eta minus eta sine theta equilibrium. All right. So we can rearrange. So this will be minus 1 over L times g sine theta equilibrium minus a cosine theta equilibrium Oh, hey, from our equilibrium conditions, that's got to be 0. That's good. Plus eta g cosine theta equilibrium minus a sine theta equilibrium. All right. So just kind of constructing our triangle here. This is g, that's minus a. That's theta equilibrium right there. All right. So we can replace the sine of theta equilibrium with minus a over root a squared plus g squared. And the cosine of theta equilibrium everywhere we can replace with g over root a squared plus g squared. So we'll substitute accordingly. So eta double dot equals minus 1 over L g squared over the root plus a squared over the root eta. Or rearranging a little more, we get eta double dot equals minus root a squared plus g squared over L times eta, which we look at that, and that's a simple pendulum, and we identify this as our omega squared. So, to an observer in the train, we would conclude that they wouldn't, if they can't look out the window, they would conclude that the gravitational field is pointing down at an angle, and that the strength of the gravitational field is root a squared plus g squared. And like I say, they would assume that the boxcar was tilted at angle theta equilibrium. And they would assume that the plumb bob was hanging down, the floor was tilted up at theta equilibrium, just like you go to the mystery spot up in St. Ignace or something. All right, let's do another example. Let's do a particle in a central force field. Just because we've already found it, let's use it. So the obvious coordinates are r and theta. We got that t was 1/2 m, r dot squared plus r squared theta dot squared, and v was just some arbitrary v of r. So the Lagrangian is t minus v is 1/2 m r dot squared plus r squared theta dot squared minus v of r. All right, so we'll have two equations of motion. The first one will be partial L partial r minus d dt of partial L partial r dot equals 0. All right, so the partial L partial r bit here. We've got two terms that contribute. The first is this one here. So differentiate that, bring down a 2, cancel the half. I get m r theta dot squared. The second term is just going to be minus partial v of r partial r, which we recognize as being our force. And then, let's see, differentiate with respect to r dot is going to give me a m r dot. Differentiate that with respect to time gives me minus m r double dot equals 0. So I can write that as m r double dot equals m r theta dot squared plus f of r. So this is our axial force, and this is our centrifugal force. All right, let's see what the theta equation of motion gives us. So partial L partial theta minus d dt of partial L partial theta dot is also 0. Well, there's no theta dependence whatsoever in the Lagrangian, so the first term is just plain 0. The second term, differentiate with respect to theta dot, is going to give me mr squared theta dot. Differentiate that with respect to time, I get minus mr squared theta double dot equals 0. Or I can write this as d dt of mr squared theta dot equals 0. And I do that because this is the angular momentum. So we get that the angular momentum is conserved here. And the way to notice that is if you look at the Lagrangian, you see that there's no theta. Since there's no theta, when I differentiate the Lagrangian with respect to theta, I'm just going to get a 0 for doing that operation. We call that an ignorable coordinate because there's no theta to differentiate. So that means that this, whatever this is going to be conserved. So if there's a variable missing from the Lagrangian, there will be something conserved. This is an application of a much more powerful thing called Noether's theorem, which is due to Emmy Noether. Okay, let's bang off just one more, and then we'll call it. So let's do a double Atwood's machine. We're just going to set it up. We're just going to work to get the Lagrangian at all. Let's do a double Atwood's machine with real pulleys. So A1, moment of inertia I1, hanging off here a mass M1, then hanging down off of there, another pulley, I2, mass, and its mass is, we'll call it mass of pulley. Its radius is A2. Hanging off of that, a mass M2 and a mass M3. And believe it or not, we can do all of this with two generalized coordinates. The first one will be how far M1 has dropped. We'll just call that one X. And then the second one is how far M2 has dropped with respect to the pulley it's hanging off of. We'll call that X prime. Okay, other relevant distances in the problem will be the distance between the pulley centers. That will be equal to the length of the string minus pi A1, half the circumference there as we go over the pulley, minus x, the bit over there. By the same token, M2 is going to hang off some length L prime minus pi A2 minus x prime. All right. So with all of that, we can start writing our kinetic energy. So T equals 1/2 m1 x1 dot squared plus, so that's that. Then we'll add in the pulley, 1/2 I1. Now the omega is going to be x dot squared over A1 squared plus, we have the translational kinetic energy of this pulley. We'll have to do the rotational a bit, but plus 1/2 mp x dot squared plus 1/2 m2. Now m2 is going to be moving at x1 dot x prime dot, sorry, minus x dot. So x prime dot minus x dot squared, and mass 3 will be with a plus sign. So plus 1/2 m3 x prime dot plus x dot squared. And then we got to spin that pulley. So we pick up a plus 1/2 I2 x prime squared over A2 squared. All right. Potential energy. V equals low-hanging fruit minus mg x1. This pulley doesn't count. This one here will be minus mp times g times that distance there. L minus pi a1 minus x minus m2g. That's m1 there. Let's see, that is going to be down a distance, this distance plus x prime. So that will be x prime minus L minus pi a1 minus x. And then for this guy, we add these two distances together. Minus m3 g L prime minus pi a2 minus x prime plus L minus pi a1 minus x. Phew. So when we set this up, this is going to look utterly heinous, right? Let's say the Lagrangian is equal to t minus v, and I am just going to copy and paste terms over. Copy, paste, there we go. Next couple of terms are these guys. Copy, paste, bring it in there. Then we got this guy. Copy, paste, so plus that. And we'll copy and paste, bringing that down there. And then we've got these guys here to bring in. So copy, paste, copy, paste, copy, paste. There. And since that's minus v, I have to go through and make all these minus signs positive. All right. Well, that's something. All right. Now, that looks utterly horrendous, and it is. But something that we can at least note is in the potential energy stuff. This guy here, if we look, this L's a constant. This A1's a constant, so that pi A1 thing is a constant. L's a constant, pi A1's a constant, L prime's a constant, pi A2's a constant, L's a constant, pi A1's a constant. We can shift the zero of our potential energy to make those terms go away. So if you combine things around a little bit, group it all together, we can write the Lagrangian is 1/2 m1 x dot squared plus 1/2 mp x dot squared plus 1/2 I1 over A1 squared x dot squared plus 1/2 M2 x dot prime minus x dot squared plus 1/2 M3 x dot prime plus x dot squared plus 1/2 I2 over A2 squared x dot prime squared. And then the potential energy actually gets a little prettier-ish, plus M1 minus M2 minus M3 minus MP GX plus M2 minus M3 GX prime. All right. So that's the Lagrangian. You can't really make it any cleaner than that. So the equations of motion will be partial L partial X minus d dt of partial L partial X dot equals 0 and partial L partial X prime minus d dt of partial L partial X prime dot equals 0. All right, you'll just stick the L in there and turn the crank. It is a very ugly crank, but you gotta admit, I think at least for me, this beats the heck out of trying to set up something monstrous like this using Newton's laws of motion. It's still going to be a pill to solve, but at least we're starting somewhere. Okay, the next video we're going to take a look at generalized momenta.